Okay, so we've just seen that we just discussed how the difference, the distance between coordinate values, which we can quantify by this by delta r squared here, um, is invariant under spatial transformations, but only when we're talking about normal Euclidean space. That is normally in the non-relativistic case. Okay, that is when the velocity between the two different coordinate systems, or the velocity between two different observers, is much less than the speed of light. In the relativistic case, okay, that is when the velocity is less than the speed of light, but on the same order as the speed of light. Then this transformation, the transformation between different coordinate systems, is not invariant. That is, this would not be a constant, delta r squared, and we've seen this already because we've discussed length contraction. That's just an example of that. Okay, so the question is there some quantity which is analogous, let's say, to delta r squared? Okay, is there some other quantity which is generally invariant under coordinate transformations, even when you're dealing with relativistic speeds? Now we have kind of a hint from the things that we've already done about how to find this generally invariant quantity, and that is that if we look at what is sort of our expression for length contraction, we have that the length of an object that's moving through a different coordinate system, through a particular coordinate system, is length contracted by this factor gamma. So it's shorter by this factor gamma. Again, gamma is just the Lorentz factor, and beta is the relative speed between the two different coordinate systems with respect to the speed of light. But then if we look at the expression for time dilation, we have that it's that the time is dilated, it's increased by the same factor gamma. So in some sense, length contraction and time dilation oppose each other. Okay, so let's figure out a way to combine them. Okay, so here I've just actually written down what this invariant interval is. Okay, we call it delta s squared. Okay, we give it the symbol delta s, and it's basically just the c times the time interval, c delta t squared, minus the spatial interval, delta r squared. Okay, notice that this has units of length, because delta r has units of length, and so does c delta t. That's also a unit of length. Okay, and so if we just write out what delta r is, it's delta x squared plus delta y squared plus delta z squared. Then what I claim is that it's invariant. So that means that in any other coordinate system, okay, like the prime coordinate system, some generic prime coordinate system, then you would have that you could call it delta s prime squared, but it's equal to delta s squared. So you have basically just this interval, as defined this way, is invariant under coordinate transformations, even when you're talking about relativistic speeds. Okay, to see how this interval is indeed invariant, let's consider an example that we've seen before, actually. This is one of Einstein's Gedanken experiments. So we have Anna and Bob. Anna is in a rail car moving to the right with velocity v. So hers is the s prime frame, and we have this so-called sort of light clock, where you have a light pulse which goes up, from some light gun, hits a mirror and bounces back down where it's detected. Okay, the distance between the light gun and detector and the mirror is L. Okay, and so for Anna, she just sees the light go up and down. That's it. She sees the light go up and down. So for Anna, delta x prime equals delta y prime is equal to delta z prime is equal to 0. That is that she sees the detection event and the emission of the light pulse at the same position in space in her coordinate system.